Hello everyone. So today I'm going to talk about work that's mainly been done by Oscar Brousse, who's here, and also Charles back in London. So it's all part of a project called Heroic, which is funded by Wellcome Trust, a health-based charity, and it's about reducing health impacts of urban overheating. So just in terms of background and motivation, so as you all know, heat is a health risk, and basically I'm very interested in how heat affects mortality, so rather than sort of thermal comfort. Obviously, climate change means that the heat health risk increases in future. And a lot of the work that I've been involved in over the years, we've looked at projecting the effects of climate change on heat-related mortality and also cold mortality. And the problem is quite often that the global sort of scale climate models used just don't obviously resolve the urban surfaces. So we underestimate the impacts of climate change on heat-related mortality in future. So obviously the urban heat island, or the excess heat in urban areas, increases this heat health risk, but it's often not really attributed. And in the UK, where this study is based, we have 82% urban, and we have a growing, more elderly population, which all sort of adds to the problems for future. So the work that we do, we quantify heat-related mortality impact of excess heat in urban environments, but we also look at the potential impact of interventions to reduce this, and particularly in the context of climate change. So the methods that we use the WRF model with BEM at 1 kilometre resolution. We look at particularly hot year, which was 2018 in London, and Southeast England, which is most of the population of England, or at least a very large proportion. We use the local climate zone classification, and we validate the model against not only the UK Met Office stations, but also we started looking at the crowdsourced data as well. And we run multiple modelled scenarios, so we want to test the effects of various interventions on basically on 2 metre air temperature. And then we take the model output and then we translate that into the associated impact on heat mortality, and also look a little bit at the economics. So this is the study area. So in the middle is London, and this is the southeast of England. So you can see the big purple dots are the UK Met Office stations that we use. Very high quality, obviously, but you can see they're fairly sparse, and we don't have very many in urban areas as is traditional. So we've started using the Net Atmo stations, which are shown by the little black dots here. We do obviously have to do a bit of quality control because you have far more observations but lower quality. But we found these to be very useful. And the colours show the local climate zone classification across the area there. So this is the output from the model. So the top left shows the average 2 metre air temperature across this region for the summer of 2018. And we have a counterfactual simulation where we basically have, we call it no urban, so we just remove the urban surfaces. And then by taking the difference in temperature between the urban and the rural, in our case, we define our urban heat island. So the bottom left shows the difference in temperatures, is the maximum difference that we saw, up to around 6 degrees over that period. And then we also quantify the impacts of intervention. So bottom right shows the impact of cool roofs across the region. So we've actually, the bottom two are zoomed into the greater London area now, which is smaller than the bigger region. And then obviously translate these into health impacts. So what you can see here is now we're looking at just a point in the centre of London rather than the whole domain. And we have the 2 metre air temperature for both the urban case in blue and then the rural or non-urban case in orange. And then in the middle is the difference, showing the heat island intensity as we're defining it, reaching 6.7 degrees. And then what we do is we use exposure response coefficients. So these are epidemiologically derived coefficients which relate daily mean temperature and increased all-cause mortality. So we use one from Arbuthnot et al. In 2020, which specifically looked at 3 largest cities in the UK, including London. And so Arbuthnot found that the threshold for mortality basically starts to increase above 18.8 degrees. So from this, you can see on the bottom graph the dotted horizontal line, that's your heat health threshold. And then we calculate the number of all-cause deaths which we attribute to heat. So for the whole of the summer of 2018, we estimate there were around 780 deaths in this area due to heat. But of these deaths, about 521 we would attribute to the urban heat island. So you basically run your health impact assessment based on your urban and your no urban scenarios. So that means that about 2/3 of the total heat mortality we can attribute to the urban heat, overheating. You can think of it in a slightly different way. We can say that that's equivalent to 6,500 years of life lost. And something we started looking at is the economic valuation of just simply the mortality, the lives lost to the heat in this way. So from around 0.8 to 1.3 billion pounds. And I mentioned the other scenarios, which are the interventions. So basically what we have here is now we have only a 2-day run. So previously we had a 3-month run, but lots of simulations take quite a long time. So we're looking over 2 days. The top left is the control urban run. And then we have the effects of, in the middle, we've got green roofs, solar panels, cool roofs. And we also have the top middle is the impact of switching on air conditioning, and we also have some extra tree coverage as well. And you can see that the cool roofs, stand out as having a big impact. And something that we've been really interested in for a long time is the potential for solar panels. So on the right middle there. So what we did is we ran the model for 3 months again, but just looking at cool roofs and solar panels, because quite often we know that cool roofs do have a big impact on the local temperature, but we also would like to find out a bit more about that impact of solar. So here we've got the 3-month run again for the baseline and the rural or non-urban, but then also the effect of solar PV in pink and the cool roofs in blue. So the bottom on the left, you can see the cooling effect from these sort of scenarios compared with the baseline, and then the cumulative population exposure, showing the cooling effect for solar and cool roofs in the middle there. And then we basically attribute that again to the mortality. So what we see here is on the left-hand side, this is the number of deaths that we attribute to heat, which was the 700 and I can't remember the number now, so 780 deaths, I think. And then the proportion of those deaths that we attributed, the 2/3 that we attributed to the urban heat island, 700 and something. 520. And then the next 2 bars, the blue and the pink bars, they now represent the potential deaths avoided. So if we had cool roofs, and this is a kind of maximum cool roof scenario, we could offset around 200 and something number of deaths. And then again, by the solar panels, the pink bar is obviously smaller than the cool roofs, but it does have some kind of effect on reducing heat-related mortality. And obviously PV has a lot of, it's energy saving, so it's not just simply the overheating, but it just shows that we have this extra effect on reducing the local temperatures as well. And a lot of the work that we do, this is all about the urban heat island and so on, but we also look at indoor temperatures and how these kind of interventions feed into indoor environment. We try to look at the kind of interaction between indoors and outdoors as well. But I'll finish then just to say that the paper that it's just come out, the middle one there is kind of the most relevant here. And thanks very much, and I'm happy to take questions.
Thank you.
Thank you so much for this very interesting study. I have 3 questions. The first one, how do you explain that in your simulation, in the non-urban simulation, temperature is higher than in the urban simulation?
Do you mean very first?
No, the previous question.
Okay.
The one before now,
Yeah.
For some days you have a negative urban heat island.
You mean like this?
Yeah, which means that you have a high temperature, one you consider that London is not a city.
So this is something that we thought someone would spot. So that there is a small period where the temperature in the rural area is a bit higher. We had a look at this. We think it's just like a dynamical effect. We get some air from the south, and we think that the presence of the city kind of blocks this cooler air, whereas when you've got an urban surface, no roughness, then it kind of gets this sort of cooler plume. But there's something that if anyone's interested in looking at the data, you're very welcome. But we haven't quite. You do get this kind of effect because it's also a dynamics effect as well.
Second question: you have applied a transition function between mortality and temperature, and this transition function now is valid under specific limits. You have applied that at the urban level, fine, but you have applied also at the non-urban level, which is not inside the levels of validity of the level.
So when we you apply the coefficient to the temperature exposure, obviously it's a theoretical. When we remove urban areas, this is then a theoretical environment, but it's within the kind of limits of the heat exposure of the population. It's a few degrees different.
It's not linear.
No, but we apply the coefficient in the way that
this transition function will not be, let's say, valid under non-urban conditions.
Yeah, sure.
Okay. And the third one is to consider that the use of photovoltaic panels may reduce the temperature of the city. Do you consider the nighttime or the daytime?
We did both. So I haven't shown it here. Did you say the solar panels or the cool? Yeah, they have much bigger effect in the daytime. So
the daytime is increased.
Yeah, definitely, yeah.
So because mortality happens during the high temperature,
Yes.
the impact of photovoltaics in the city may increase mortality, not decrease. You have a lower temperature during the night, mortality during the night, because when there is lower degrees, is out, on the transfer function. So in this case, the decrease of the temperature caused by the photovoltaics during the night it has not any effect on a very minor effect on on the contrary, the increase of the temperature during the daytime because of the photovoltaics 1.52 degrees, may increase the temperature.
So on average, it would decrease the temperature.
During the day?
Yes.
I'm sorry. The surface temperature of the photovoltaics.
We're talking a 2 meter end.
In summer is 60 degrees. How a surface of 60 degrees may decrease the temperature?
Because we're talking about the air temperature, not the surface. So it does decrease the temperature. Well,
In all papers that are published, it shows that it increases the temperature, except if you consider in your work simulations that you don't have excessive heat emitted by the lower part, which is wrong.
okay. Well, maybe we look in more detail, but I'm
Thank you very
pretty
much.
sure that the solar panels and the cool roofs do.
And the grid is fine, but the solar panels, it's too far to believe that it decreases the temperature.
Well, it definitely decreased the temperature in our model. And when we take the temperature for the health impact assessment, we use a 24-hour mean.
Check the decrease of sensitive heat.
Okay. We have a 24-hour mean temperature, which relates to the mortality.
24 hours, okay, but not during the day.
But the metric is for the mortality is 24-hour mean. Okay.
I might have to.
One more quick question. Great presentation. I was wondering if you have thought of combining some of the measures, like you have cool roofs and green and photovoltaics.
Yeah.
Have you thought about scenarios of increasing green space with photovoltaics and cool roofs?
Yeah. So the common thing is to have the solar panels with the green roof underneath, and they're supposed to be very effective. We kind of recognise that it's impractical to have green roofs everywhere, cool roofs everywhere. We know that it's going to be kind of adaptive. So it's not something that we've run the model with yet. We've done them separately, but that would be definitely, we would try to sort of tailor it a little bit more. Thank you.
Thank you. All right, our next speaker will be Leslie from MIT talking about anthropogenic heat. Let's welcome.